Hail resistance, this is Pradesh Chaudhary Quantum Group. Let's see this network of resistors in the shape of pyramid. The resistance between any two nearest nodes is R, and we have to find equivalent distance between A and B, A and C, and A and D. In fact, resistance between A and B would be same as between B and C, between C and D, and between D and A. And the same way, resistance between A and C would be same as between B and D. And resistance between any corner of the base and any top corner would be the same. So effectively, by taking these three pair of points, you can find in fact resistance between any two pair of points. All right. So let's go ahead. First, I want to simplify this diagram. This is a 3D diagram. Base is a square and this is a pyramid. I want to convert it into a 2D diagram. So what I want to do, I just want to compress this whole diagram and want to put this point E at the center of the base. So the diagram will be reduced to this. This is A here, B here, C here, D here, and E has come to the center of the base. Now this looks pretty easy, and you can see a lot of symmetry, and we can go ahead to find the resistance between the required points. So between A and B, these two are the points. So I have sent a current I at the A, and the current I leaves from B, and immediately we can see symmetry here. So what symmetry we can see? The symmetry that you can see here is this. This is a line, and we call this perpendicular to line of symmetry. So if this is a line, you can see that the elements on the left side of this line and on the right side of this line are the mirror image of each other. And what I have done, this is R. I have conveniently distributed this R into R by 2 and R by 2 because of the series combination, and same here. So in that way, you can see that for this hypothetical line, you can see the elements on the left side and elements on the right side are the mirror image of each other. And what does that mean? If these elements are the mirror image of each other, this is the entry point and this is the exit point. So the symmetry will require that if this current is X and this current is X, and obviously it has to be because there is no bifurcation of here. But clearly, because of the mirror image being these two parts being mirror image, same way, if this current is Y, the current goes this way, so the current has to come this way, and that is Y. And the same way, if this current is Z, and this current should be Z, and if this current is P, so should be this current, and if this current is Q, so should be this current. So what does that mean? So you can see that this is a Z and this is Z, this is Q and this is Q. So in fact, there is no part of this current goes to this part, and this current goes totally like that. And the same way, this current goes totally like that, because this is Z, this is Z, this is Q, this is Q. So though there is a physical contact here, that is not electrical contact, no part of this current goes to this part. So the current goes this way and this current goes this way. So I can just make it like that. This current goes this way and this current goes goes this way. So I can reduce this diagram to this diagram. Just I want to separate these the point E like that. So now that is a very simple thing. So first of all, this R and this R and R will make 2R. So this 2R and R will parallel combination will give 2R by 3. And this 2R by 3 is in turn in series with this R and this R. So that would make 2R by 3 plus 2R is equal to 8R by 3 up to here. So from here to here, these whole resistances are 8R by 3. And the same way, this 2R and this R is in parallel, and that will make 2R by 3. So from here to here, that whole thing is 8R by 3, and this is 2R by 3, and these are in parallel. So overall, equivalent resistance between A and B is the parallel combination of 2R by 3 and 8R by 3. 8R by 3, this is basically 8R by 3, and if we simplify that, and we are going to get 8R by 15. And we also had to find the resistance between A and C, and that is the diagram. So let's just reorient this, rotate this diagram by 45-degree clockwise, and we'll get this diagram. And you can see a lot of symmetry here. So the symmetry here, you can see that this is A is the point where current enters and C is the point where current leaves, and this line is the line of symmetry. How it is that? Clearly the elements above this line of symmetry and below the line of symmetry are mirror image of each other, so that's why it is a line of symmetry. And what happens if there is a line of symmetry? So diametrically opposite points are at the same potential. So what you can do, you can just rotate this circuit, fold this about this line AC, and B and D would be at the same point. Or you can also see that this is also line of symmetry, because the elements on this side and this side are mirror image of each other. And because first of all this is a line of symmetry and this line is perpendicular to line of symmetry, so we call it perpendicular to line of symmetry, that is PLOS. Okay, so this is PLOS. And what happens in the PLS? All the resistors that are PLS we can simply remove. Why we can remove? Very clearly. So because of the symmetry, whatever current comes here, the same current will go there. Whatever current comes here, the same current will go there. So no part of this current will come to this resistor, and no part of this current will come to resistor. So we can simply remove these two resistors. Alright. So now the diagram would be reduced to this. I have removed this and this. So effectively this is a parallel combination of this 2R, this 2R and this 2R, and that will make 2R by 3. And finally we have to find the resistance between A and E. So this is A and this is E. So once again just flip this by 45-degree like this, and you can see that this is a line of symmetry because elements on this side and this side are mirror image of each other. So if this is a line of symmetry, this is a line of symmetry, so obviously by the symmetry the same current will go to this part and this part, because these two currents are the same, starting from the same point, they will suffer same potential difference from here to here and here to here. So B and D would be at the same potential. So we can just simply join B and D by folding the circuit about line AC, which is line of symmetry. And if I fold it about AC, B and D will come at the same point. So what will happen? We'll get this diagram. So here you can see that this is A, this is E, this is C. So this R is in place of this R. And here now if D and B will come to the same point, this R and this R will be a parallel combination, that will make here R by 2. Same, this R and this R parallel combination will give R by 2, and this R and this R parallel combination will give R by 2. Now this is a very simple thing. So we'll do step by step. So this R and R by 2 series combination will give 3R by 2, and this 3R by 2 and this R by 2 are in parallel, so that will give 3R by 2, and R by 2 parallel will give 3R by 8. And up to here whatever we got 3R by 8, that is in series with this R by 2. So that makes 7R by 8. So up to here this and that in turn is in parallel with R. So finally we'll get RAB is equal to parallel combination of 7R by 8 and R, and simplify it, we will get 7R by 15. That would be our answer. Thank you.